In part two, we're going to look a little bit more deeply at NMR, some of the reasons why some of these phenomena occur, and then we're also going to give a couple of example spectra. So ultimately, why does the unique environment change the position of the NMR signal? All right, so recall that we are working with hydrogen 1 NMR, and if we had these just individually in solution somehow, let's just say hypothetically that these are all just by themselves in solution, not attached to anything else, they would all absorb at the same position. However, we know that that's not the case, that these hydrogens are attached to other atoms. So if we take something like just CH4, methane, all right, so the hydrogens are all attached to carbon, and that ultimately being as part of a molecule will influence the signal. All right, so really what happens in something like CH4? Well, the electrons around the nucleus ultimately reduce the total magnetic strength. So the electrons are around the nucleus of that hydrogen, let's say. Really, it's all four of them, but we'll just pick on that one. So again, recall what happens is that when we take an NMR of these molecules, we put them into a magnetic field. This is the external field here, which we call HO. As a result of being in a magnetic field, we see that we have the nucleus where the proton is in the hydrogen. We also have an electron cloud circulating. All right, so it's circulating under the influence of HO, as they say here. All right, so what happens, though, because of this electron cloud that's circulating, it basically opposes the HO, the field. And so this sets up what we call a local field, sort of in opposition to this external field. These electrons move in this direction, create a field that's in opposition and opposes it. And so we would say then that the proton is then shielded. All right, so it's shielded from the full effects of the external field. All right, because why? Well, the electrons are moving in a way that's opposite ultimately to the field, and it's opposing. And so this proton here is not feeling the full effects, and so we say that it's shielded. Well, what happens is that we can have a situation where we can have some of those protons that are de-shielded. All right, so we can actually remove some of this electron density, and that would de-shield them, and they feel the fuller effects of this external field. For instance, instead of if we had methane, let's say we had chloromethane. So replace one of the hydrogens with this chloro group right here. All right, so we know that chlorine, chloro atom that's attached there, is electronegative, and so it ultimately pulls some of the electron density from these hydrogens. Not all of it, but because it's electronegative, it's pulling electrons through the bonds. And so this field here of electrons, or this electron cloud, is not going to be as strong. There's not going to be as much electron density because it's been pulled away, it's been de-shielded, and so then that opens up the nucleus here to the fuller effects of this external field. All right, and so because this is in as opposition, this proton in the nucleus here is feeling the full effects, or the more full effects of the external field, so it's held more tightly, and so hence it will require more energy to actually change the position, flip it from alpha into the beta position of this particular proton. All right, so that's how these hydrogens then would be different than these four. All right, so even though and it really doesn't have anything to do with 3 and 4, it has to do with the fact that we have this chlorine here. It's pulling those electrons, it's de-shielding it, and so the hydrogens that are on this molecule would be more fully held by the magnet, and they require a greater amount of energy to actually flip them. So that's why then we would have a different position of different hydrogens in molecules. All right, and it has to do with how much they're shielded and ultimately de-shielded because of the makeup. All right, so that's really the reason why we have so many different positions that hydrogens can show up in an NMR field. This table, 10.3 from your textbook, helps to highlight that. All right, so again, if we go back to methane, notice that we look here again. It's going to have a hydrogen that show up. It's about 2.2, and I'm sorry, the hydrogen's 2.2, but it's going to show up here. The chemical shift of the CH3 is about 0.23. All right, so noticing the electronegativity of that hydrogen. Well, if we go to iodine, which is a little bit more electronegative, notice 2.7. the chemical shifts ends up at about 2.6. All right, so it's further downfield. You might remember we called that. And then bromine, chlorine, these guys, notice as the electronegativity goes up, then further downfield the shift goes. All right, so it goes further from that 0. So you might remember that if we had our 0, and this is our parts per million down here, delta, 1, 2, 3, is that initially here, again, we would have this peak at 2.3 or so. It's approximate. Notice for that, if we have it in the presence of fluorine, then it's all the way down here. Didn't even put 4 on the scale on this one. And then this is where the peak would show up. All right, so again, further downfield this way. Why? Because the fluorine has greater electronegativity. It's pulling the electrons away more fully from these hydrogens right here. And as a result, then they feel the fuller effects of the magnet, and so it requires more energy, and that they're further downfield downfield because it requires more energy to actually flip them from the alpha into the beta position. All right, so again, really more electronegative atoms will ultimately do that. Just going back to our same molecule that we've seen before, and you might think about this in terms of a couple of things that we've just talked about in terms of electronegativity. So noticing that we have this CH3s, and again, what is nearby? Well, we have a carbon and then also some hydrogens that are here, so those are all not so electronegative, so the methyl groups appear pretty close to where we would expect them, between 0.8 and 1. Notice, however, these hydrogens, not only do they have the carbon and those red hydrogens nearby, but they have this oxygen atom, which is electronegative. And remember, oxygen was sort of close to the top of that last table, and so those are de-shielding these electrons to a greater extent, making them have further absorbance downfield. So notice it's here, CH2, and again, it's because they're here. And then notice in the alcohol peak is right here. Again, it's also attached to an oxygen, and so it's further downfield than we would necessarily expect. And ultimately, this OH peak is variable. It can be anywhere from about here all the way down to 5, and that it's dependent upon really the environment that it's in. So that's a little bit complex. But the key is that because these blue hydrogens are adjacent to this oxygen, it pulls them downfield to where we might all expect them right about 1. Okay, so let's take a break. Think about this. How many different types of hydrogens do we have in this molecule? And this is just sort of helping us review this problem. So take a second to think about that. How many different types of hydrogens? Think about different environments that we have in this one. All right, so if you said 2, you're correct. This would be 1, we'll call it 1. And then all of these hydrogens right in here, those would all be a second type. They're all the same environment. Because what we ultimately see is we have these guys. They're all CH3s, all attached to carbon OH, so they're really in the same environment, and this is the one that's different. So really there are 2 different types. Another question, is this a thumbs up or thumbs down statement? Is this a correct statement or not? We would say that the peak at 2 parts per million right here is upfield from the 1 at 1.3. All right, so that would be a thumbs down because we would say that this is downfield. All right, so the peak at 2.0, or about 2 parts per million, is downfield from the 1 at 1.3. All right, and so we would say that 1.3 is upfield from 2. All right, so just a couple of review questions about some of the things we've talked about. We've also mentioned already previously, we talked about the 4 bits of information that we get from a spectrum. One of them was integration. All right, and so ultimately integration reveals the number, and so sometimes when the computer program and we figure out how many protons are there, you might write that number, the computer might write that number right above the peak, so it might put a 9 there, and a 1 there, and a 2 there. Another way that this would happen would be that the computer draws these lines. All right, so sort of draws this integration, and that you would ultimately just measure, either you'd have the computer measure like how tall this little line is. In the old days you had to measure that, and then you could actually get a relative. So noticing that the 1 hydrogen the line goes up 2.5 millimeters. Notice this one's double that one, it goes up 5 millimeters because there are 2 hydrogens, and then notice that this one's 22 because there are 9 times as many. All right, so but nonetheless, you can get the integration. Sometimes it's written right above the peak. Sometimes you get this type of thing, which shows you, and then sometimes you can just sort of look at the area under those peaks and figure which ones how many are there. You get it out, just sort of a relative amount. All right, so that's integration. One of the things that we've not talked about yet is spin-spin splitting, and that's the effect of non-equivalent neighbors on hydrogens. All right, so let's focus to understand this on these 6 red hydrogens and how one non-equivalent neighbor, splits the signal. Well, first of all, let's describe what we mean by a neighbor. All right, and so these 6 red hydrogens, they're all within 3 chemical bonds of this non-equivalent blue hydrogen. So 1, 2, 3. And so we're going to say that they are neighbors because they're basically close by. Just like you might have a neighbor that's nearby. Someone across town may not be really what you might consider a neighbor, but someone who lives next door, those would be a neighbor. And that's really what's happening. So this red hydrogen, 1, 2, 3 chemical bonds to that hydrogen. Same thing with this one, 1, 2, 3. So we're going to say that those are neighbors or neighboring hydrogens. Now, if they are non-equivalent neighbors, all right, so because these red hydrogens are close by to each other, 1, 2, but they are equivalent, they're chemical equivalent. But if they're non-equivalent neighbors within 3 chemical bonds, basically they can split the resonating resonance into a doublet. All right, so these 6 red hydrogens are going to be their combined signal of all 6 of them together are going to be split into a doublet because they have one non-equivalent neighbor. All of these are within 3 chemical bonds of this hydrogen. All right, so we're going to be split into a doublet, and this is known as the N+1 rule. All right, so these 6 red ones have this one hydrogen, so that is non-equivalent. It's within 3 chemical bonds, so one of those, N equals 1, 1 plus 1 is 2, and that results in a doublet. And in fact, if we look at the signal here of the 6 red hydrogens, show up about 1.8 or 1.9 or so, notice that we blow it up so we can see the detail. They're split into a doublet. Well, the same thing occurs, though, with this blue hydrogen. It's within 3 chemical bonds of 6 non-equivalent neighbors, 6 non-equivalent hydrogens. So N is 6, 6 plus 1 is 7, and so its signal is split into 7 peaks, which again, if we blow this up, occurs right here. Now, this might be just a little bit challenging to count all 7 of these, but I'll try to point out that on the outside, right about above the black dot I've made, are these little tiny just peaks. All right, so if we count those 2, and then 2, and then 4, and then 6, and then one big one in the middle, that's 7. All right, and so this is referred to as a septet or sometimes a multiplet because there are 7 of those. All right, but nonetheless, this is the N+1 splitting. It results because you have this one hydrogen, and again, it's in a different environment, or it has a different amount of shielding and deshielding as a result of this iodine compared to these. So it's a little bit further downfield, and then also its signal is interfered with by these 6 non-equivalent neighbors that are next door. All right, so as a result, then its signal gets split 7 times. And then same thing is that the signal for these 6 hydrogens, they're split into a doublet. All right, so that's a little bit of our spin-spin splitting. Let's take a further look at that. Before we talk about this coupling constant, let's just review with this bromoethane, the spin-spin splitting. All right, so we have these 3 red hydrogens. They're within 3 chemical bonds, 1, 2, 3, of 2 non-equivalent neighbors. All right, so again, the 2 non-equivalent neighbors, that's going to be N plus 1, so 2 plus 1 is 3. All right, so the signal for these 3 red ones are going to split into 3, and that's exactly what we see. If we pull this up, it comes right here. We have 1, 2, 3 peaks in its signal. Well, also, these 2 blue hydrogens, they're within 3 chemical bonds of these 3 red ones, and so that N value is 3 because there are 3 non-equivalent neighbors, so N equals 3. 3 plus 1 is 4. And notice that the blue hydrogens have their signal split 1, 2, 3, 4 times. All right, so 4 peaks in their signal. All right, so hence the N+1 rule applies with these. Now notice that the distance between all of these peaks is uniform. All right, so if, the peaks aren't all the same height, but they're all the distance in between those are all the same, even up here. And so that distance is what we call the coupling constant, and we measure that distance in hertz between the individual peaks, and then we give that the term J. All right, so the individual letter to figure that out. And so the goal of this slide, and for us just to know that this coupling constant exists, to be able to define is that really that distance or the space in between those peaks, and we measure that space or that distance in terms of hertz. But this also helps us to see then the n+1 rule, the spin-spin splitting. Let's take a look at one spectrum of a molecule that's a little bit more complex. And a couple of things, remembering that we get 4 bits of information. We get the number of peaks, the number of signals, which are shown by these 4 sets of signals. We also get integration. We see the integration that's here. That's often shown on this. We get chemical shifts. Notice that these are all different chemical shifts. And then we also get this spin-spin splitting. So these peaks are split. And this one's not, but we'll talk about that. So let's just approach this spectrum. Again, starting from here and moving sort of downfield, A, B, C, D. Just note in this particular spectrum, we do not have a peak that's at 0. Remember, we often see that, and that's known as TMS, and that helps to set up and to set the spectrum at 0. That is not shown here, but it often is. So, peak A. Peak A deals with these hydrogens right here, and there are 6 of them. All right, so again, we see that the integration here is set up at 6. We also get the signal at about 0.8, and that's fairly typical for methyl groups, about 0.8 to 1. So we got that part of it. We get the chemical shift, and then also these 6 hydrogens, 2 sets of methyl groups, are within 3 chemical bonds, 1, 2, 3, of one other hydrogen. All right, so there would be 1, 2, 3. They were not quite connected to those 2, so it's 1, 2, 3, just to this one hydrogen, which we've labeled B. So they have one non-equivalent neighbor nearby. N+1 is N. 1 + 1 is equal to 2, and so occur as a doublet, and in fact we do see that here. All right, so we have, this is one of the 4 signals, integration of 6, which we see, chemical signal about 0.8, and then spin-spin splitting into a doublet. Moving over here, we'll look at this hydrogen B. All right, so again, it's a second signal. We get also its integration. Notice it's not exactly 1, but it's pretty close, 0.9. Remember, these are all measurements, so a little bit of error there, so 0.9. And then we get the fact that it is a methyl group, in terms of tertiary, not a methyl group, but it's a tertiary group, so there's 1, 2, 3 of those. So those occur a little bit further downfield, and so that's about right for a tertiary hydrogen that's sticking there. And then we get our spin-spin splitting. So within 3 covalent bonds of this guy, we have 1, 2, 3, so we have 6 of these, but then we also have 1, 2, and then a hydrogen that's shown there. And so then that gives us a total of 8 non-equivalent neighbors. And so we have 8 plus 1 is 9, and so the number of peaks here are 9, and so we see this as 1, 2, 3, 4, 5, 6, 7, 8, 9, and so we see that those are shown there. And so that's important, so we get our spin-spin splitting from that one. So we have, it's a signal, integration of 1, we get the chemical shift, which is about here, and then also the spin-spin splitting. We'll move over here to C, which appears here. Notice it's an alcohol peak. Again, shows up about here. Notice that we see that integration of 1. It would be within 1, 2, well, actually 1, 2, 3 chemical bonds of these 2 hydrogens, which we've labeled D. But notice there's no spin-spin splitting. Why is that? Well, these are acidic, and they exchange with the solvent, so there's no spin-spin splitting which occurs for them. All right, so that's something that's fairly unique to OH groups, and so we see those here. And so just know that whenever you have an OH peak, because of this rapid exchange, we get no spin-spin splitting. All right, and then finally, we have D. We have these guys. Again, notice that they are here. There's a signal. They're pretty far downfield. Again, why? Because they're connected to that OH, and because that oxygen's fairly high on our list of electronegativity, it moves them down the field. In terms of the spin-spin splitting, well, actually, let's go back to integration. There's 2 of those, integration, get those. But as far as the spin-spin splitting, they would be within 3 chemical bonds of that OH, But again, because of this rapid exchange of this H group here, it does not split them. So these hydrogens, which we label D, are only split by this hydrogen B. So hence it's a doublet. And so we see that it's a doublet there. All right, so we have that. So again, going back, reviewing again as we did at the beginning of this slide, we get chemical signals. We have 4 different chemical signals that occur. We get integration for each one of them. Their chemical shifts match up fairly well to what we see in our chart. And then for each one of them, we get spin-spin splitting. And for the fact that we do not get spin-spin splitting for this guy, that's okay, because this actually gives us some information that the fact that it's an OHP. Because this lack of splitting is unique to the hydrogens. And so we get all of our 4 bits of information from this spectrum. And so you want to be fairly comfortable with looking at a spectrum such as this and being able to interpret and being able to pick out, say, given 3 molecules, which spectra goes with which molecule, or identifying a compound based on its spectrum. And you're going to get opportunity to do this both in some of the lecture material and the laboratory material.